Dear students, in this video on current electricity, we will study about electrical energy, power and numerical problems based on them. So let us begin with the idea of this electrical energy. It is the work done by current while passing through a conductor, or it is the energy consumed in an electrical circuit. So let us take this conductor AB, which is carrying current I for say time t. Now point A is at higher potential VA, point B at lower potential VB. You know that current always flows from higher potential to lower potential, and the potential difference between these 2 points is V. So now let us find out a relation for this electrical energy. So you know that the work done is Q into dV. dW is equal to Q dV. So the work done W is equal to Q and V is the potential difference V, and Q is equal to current into time. Charge is equal to current into time and V as it is. And in place of this V, we can write IR using Ohm's law. So W is equal to IT into IR. Simplifying it, you get I square RT. Now in place of I, you can write V upon R. You know Ohm's law, V is equal to IR, right? So, and RT outside, simplify it, you get this relation. So the final relation that we obtain for work done or electrical energy is VIT or I square RT or V square upon R into T. Okay. So now let us define electrical power. Electrical power is rate of consumption of energy in an electrical circuit. Its SI unit is watt. Symbol used is capital W. So the power is work done per unit time, that is VI is equal to I square R or is equal to V square upon R. Now the question arises that in which situations you are going to use these different formulae. So we are going to discuss that only. Let us take a series combination of two resistances R1 and R2. Now in series combination, current through each component is same, right? And in this case, we will use this relation I square R. See, the work done W is equal to I square RT and P is equal to I square R. Now we are going to use these relations for series combination. Okay. Now what happens in parallel combination? See, in parallel combination, all the components are connected in parallel to the source of electricity. Now here current I is taken from the cell or battery, and at this point I1 goes to a resistance R1, I2 goes to resistance R2, and then at this point these two currents meet and current I is returned back. So the potential difference across each component is same, and in that case we use this relation V square upon R into T for electrical energy, and for power we use V square upon R. So we use power as V square upon R in parallel combination. Now a very important point. In household circuits, all the components are connected in parallel. So all the items at your home, whether bulb or fan or whatever, they are designed to work at 220 volt, which is the power supply in your homes, right? And they all work at they all are designed to be connected in parallel only. Okay. So power in series combination. Let's see what happens in series combination. We have two resistances connected in series with a source of current, right? Now here you see current passing through each resistance is same. say we have these two bulbs R1 and R2. Now you know that these bulbs are available in market and they are designed to work at constant voltage. It can be 220 volt or 230 volt for a house supply, right? So you know that power P is equal to V square upon R, or R is equal to V square upon P. Just change the sides, you see, right? So this resistance R1 is V square upon P1, resistance R2 is V square upon P2, and the equivalent resistance in the circuit is R1 plus R2. And if the equivalent power in the circuit is P, then this equivalent resistance will be equal to V square upon P. Now putting these values in this equation, we will get R is equal to V square upon P is equal to R1 V square upon P1 plus R2 V square upon P2. And you can see that V square is common on both the sides. So we can easily cancel this V square upon both the sides, and we get this relation that 1 upon P is equal to 1 upon P1 plus 1 upon P2. So in series combination, the consumption of power decreases. This net power P is lesser than P1 and this P is lesser than P2 also. Okay. So in series combination, the power consumed decreases. Now let's see what happens in parallel combination. Here we have a source of current as V and two components R1 and R2 are connected in parallel. You can see. So here see, this current I is drawn from the source, and at this point junction rule is applied. Current I1 goes to R1, I2 goes to R2. At this point again I1 and I2 meet and current I is returned back to the source, your supply, right? And potential difference across each of these is constant. So supposing say this is a bulb, it is working at 220 volt. This is another bulb or fan working at 220 volt supply, right? So you can see that the total current I is equal to I1 plus I2, and you know that V is equal to IR, Ohm's law. So from here I is equal to V upon R. So I is equal to V upon R, that is equal to I1 V upon R1 plus I2 V upon R2, right? And you know the relation for power is V square upon R. So to make it power, we multiply the whole equation by V. So we will get V square upon R is equal to V square upon R1 is equal to V square upon R2, right? And now this term V square upon R is the total power consumed in the circuit. V square upon R1 is power of the first resistance. V square upon R2 is power of the second resistance, right? So in this way, the total power consumed in the circuit is sum of these two powers. So powers are added in parallel combination. Okay. So now let us solve some numerical problems based on them. And to begin with a very simple one. Two electrical bulbs have the following specifications: 100 watt at 220 volt, 40 watt at 220 volt. Which bulb has higher resistance, and find the ratio of their resistances. Now you have this relation, R is equal to V square upon P, or P is equal to V square upon R. See? So since V is constant for both of them, I can write R is inversely proportional to P. So that means the bulb with lower power will have higher resistance. So the bulb of 40 watt will have higher resistance. And to find their ratio, you see, R is inversely proportional to P. So R1 upon R2 will be equal to P2 upon P1. See, inverse relation is there, right? Now, P2 is equal to 40 watt, P1 is 100 watt. Simplify it, you get this relation. So the first question is done. Now let us move to the second question. A very interesting one. Okay, see. Two heaters of rating 300 watt and 200 volt and 600 watt 200 volt are connected in parallel to 200 volt supply. Find the total power consumed. Right, so first thing, they both are designed to work at 200 volt, and they are connected to 200 volt supply only. So the total power consumed, we just learned that in parallel combination they are simply added up. So you get 300 plus 600, that is 900 power. So the total power consumed in the circuit is 900 watt. Now the second part is, which heater will consume more current? And for this we must find out their resistance and resistances of heater. Now see, R is V square upon P. V is 200 volt. So 200 into 200 upon 300 for the first heater, or 400 upon 3 ohm. R2 is V square upon P2. So 200 into 200 upon 600. 600 watt is there. That is 200 upon 3. So you can see that the heater with lower power has greater resistance and heater with higher power has lower resistance. Okay, a very important thing. And now let us look at the currents. Now current in 300 watt heater. Now I is equal to P1 upon V. We have done that P is equal to V into I. Right? We know for each of the components, and power of every component is given. We can find out the current passing through them. Right? So now I is equal to P1 upon V. P1 is 300 watt. V is 200 volt. So it is 1.5 ampere. And current in 600 watt heater is P2 upon V. And see, P2 is 600 watt. V is 200, that is 3 ampere. So one thing is clear, that the heater with lower power rating consumes lesser current and heater with higher power rating consumes more current. So parallel combination में ज़्यादा पावर रेटिंग वाला ज़्यादा करंट लेगा, कम पावर रेटिंग वाला कम करंट लेगा, और ज़्यादा पावर रेटिंग वाले का रेसिस्टेंस कम होगा और कम पावर रेटिंग वाले का रेसिस्टेंस ज़्यादा होगा. Now a similar problem but in a different situation. Now heaters of rating 300 watt 200 volt and 600 watt 200 volt are connected in series to a 200 volt supply. Now remember, here we are connecting in series the same heaters. Find the total power consumed and which heater will produce more heat. Now in series combination, the power is given by this relation. 1 upon P is equal to 1 upon P1 plus 1 upon P2. That is 1 upon 300 plus 1 upon 600. You simplify it, the power comes out to be 200 watt. You see, this 200 watt is lesser than this 300 watt and it is lesser than this 600 watt. So the net power consumed has decreased, as you can see. Now resistances of heater that we have just found out. For R1 it is 400 upon 3. For R2 it is 200 upon 3 ohm. So since they are connected in series, the total resistance in the series is R1 plus R2. See, we need to find out the current in the circuit. We have two resistances connected in series to a source. This is 200 volt, right? So we need to find out the current passing through them, and for that we need to find out the total resistance in the circuit. Remember that this is a series combination. So total resistance in the circuit is 400 upon 3 plus 200 upon 3 ohm, and simplify it, you get 200 ohm. So total resistance in the circuit is 200 ohm. Total current in the circuit will be V upon R, that is 200 upon 200, that is 1 ampere. So 1 ampere current is flowing through each of the resistances, each of the heaters. So the power consumed by 300 watt heater will be I square R, and I is 1 ampere, so 1 into 1 into R is 400 upon 3, that is 400 upon 3 watt. Power consumed by 600 watt heater, the second one. Now this is going to be, look at it, the power consumed by the second heater is again I square R, 1 into 1 into 200 upon 3. Its resistance is 200 upon 3, that is 200 upon 3 watt. So what we notice here is that the heater with lower power rating consumes more power than the heater with higher power rating. जो 300 वाट का हीटर था वो 400 अपॉन 3 वॉट पावर कंज्यूम कर रहा है, और 600 वॉट का हीटर था वो 200 अपॉन 3 वॉट का पावर कंज्यूम कर रहा है. तो क्लियरली जो हीटर ज़्यादा पावर कंज्यूम करेगा वो ज़्यादा गर्मी देगा, ज़्यादा हीट देगा. सो 300 वॉट का हीटर जो है वो ज़्यादा हीट देगा और 600 वॉट वाला कम हीटर देगा. दैट इज़ रियली अ फनी थिंग हियर, दैट जब आप सीरीज़ कॉम्बिनेशन बनाते हो तो जो कम पावर रेटिंग वाला जो हीटर है या बल्ब है वो ज़्यादा एनर्जी कंज्यूम करेगा, ज़्यादा हीट देगा, और ज़्यादा पावर रेटिंग वाला कम एनर्जी कंज्यूम करेगा और कम हीट देगा. राइट? सो आई होप दैट these ideas regarding electrical energy are clear to you, and with this we come to the end of this topic. Thank you very much for watching this video.